Okay, so this problem here deals with collisions and projectiles. So that's going to be some kinematics and some momentum conservation. And the key in this problem is really figuring out which one of those tools you can use to answer any problem based on sort of the information you're given and what you're being asked to find. So first, we have a straight line collision. Right? We have one object moving, and it hits another object that's at rest, and the object that's at rest then starts moving and falls off the table. And we want to figure out first how fast that target, right, ball B, how fast does it move right after the collision? Right, and so when you see something about immediately after the collision, that should be a sign that you think of momentum conservation. Right, we aren't talking about it traveling for some time or for some distance, so kinematics doesn't make a whole lot of sense. We don't know anything about the forces involved, so talking about Newton's laws and accelerations doesn't make a whole lot of sense. But immediately after the collision, that means in collision momentum is conserved, and that might be a useful tool. So that's what I'm going to start with. So we're going to say P initial equals P final for our system, which is for balls A and B together. So we need ball A and B's initial momentum. We know ball A is mass, 0.1 kilograms, and speed, 1.4 meters per second. I'll leave off the units just to save space. Ball B is initially at rest, so initial momentum for it is 0. After the collision, we're told the incident ball, so incident means the incoming one, or the one that was moving at first, ball A, that one rebounds. So rebounds means bounces back the way it came. So if I'm going to draw a picture of like what it looks like after the collision, actually, we'll make that our before picture. After the collision, right, that one's moving this way, but we're told ball A rebounds. It comes back the way that it came from. And so our final momentum for ball A is the same mass, right, that doesn't change, times a negative 0.7 meters per second, right, backwards, the direction changes. Then we need the momentum of B after the collision. We know its mass, and we want to find its velocity. And that's our unknown. And so now we have an equation that has one unknown and we can solve, right? So we clean this up a bit. Right? And we get that V final is going to be 0.42 meters per second. Okay, good. So there's part A. So now we deal with what comes after that. So the collision is finished, and we know ball B's speed, and we want to figure out how far does it travel horizontally before it hits the ground. What that's drawn as distance little d on the diagram. And so this one is a kinematics question. Right? This is projectile motion. Right? It's moving in two dimensions at once, horizontally and vertically, because it's falling and it's got its initial velocity from after the collision. And so once you recognize it's projectile motion, you should kind of know what steps to take into account, right? We have to do something with the vertical part and something with the horizontal part. And since our final unknown is in the horizontal part, we should probably consider the vertical part, right, first. And so in the vertical motion, we know exactly how far it travels, 1.2 meters. And we know its initial velocity, right? V initial y equals 0. Y final is 0 on the ground. Y initial is a positive 1.2. We know the acceleration, right? Negative 9.8, because it's downward. And so we can use this information to figure out how long is it in the air. That's a kinematics relationship, right? So I'm going to take the quadratic one, because that's got the one that's got acceleration in it. So y final, or sorry, so 1.2 equals 0 plus 0 for the initial y velocity, plus 1/2 negative 9.8 t squared. Right? Oh, sorry, this is... Oh, I did flip that here. Let me rearrange that. So we have to write y final, which is 0, and y initial is 1.2. I wrote them backwards. So if you solve this for t, the negatives will go away, which is good because you have to take a square root, right? Moving this to the other side will give us a second negative to cancel the negative at 9.8. And so if we do that, we're going to get that t equals 0.49 seconds. So this is not something that's asked for, but you can't solve the problem without it. It's an intermediate step. We now know how long the ball is in the air. So now we can use the horizontal part. Right? We know our initial horizontal velocity. That's what we just found in part A. We know where we start. Right? Our unknown is how far do we travel. And we know the acceleration is 0 because that's horizontal motion. There's no horizontal forces. And we just figured out how long we're in the air. So we're going to use the kinematics equation that we just used again. So x final, d, equals x initial, 0, plus v initial, 0.42, times t, plus 1/2 at squared. But a is 0, so that's all just 0. And so this is a very, very simple equation to solve. And we find that the distance we travel is 0.21 meters, right? And that's our answer, right? This one, the trick to it is recognizing that it's a multi-step problem. We have to use the vertical information to find the time, and then the time and the horizontal information in part A to figure out the distance. Okay, so on to part C and D. So now we've changed the experiment slightly. That no longer is it just moving in one direction on the tabletop, right? Now we have a collision in 2 dimensions, right? If we make our tabletop looking straight down as they do and call that our XY plane, after the collision, ball C is moving in both X and Y directions. So it's a bit more complicated of a collision. And then once it leaves the tabletop, it's still projectile motion like before, right? That part hasn't changed. Once the collision is completed, nothing is different. So part C asks for calculate the speed of target ball C immediately after the collision. And your first instinct, most likely on seeing this, is, this is exactly like part A, right? We had to calculate the speed of the ball right after a collision. We need to do momentum conservation. There is one problem with that. If you want to do momentum conservation, we need to be able to describe the momentum of everything before, which we can do, right? Ball A's momentum is fully known before the collision. Ball C's momentum is fully known before the collision. Great. But after the collision, we aren't told anything about ball A's final velocity. So we don't have enough information. We have 2 unknowns in our momentum conservation statement. We don't know ball A's final velocity, and we don't know ball C's. So we can't use momentum conservation to find it. We have to find something else. And as I look at the problem, I see that there's one piece of information that I wasn't given in parts A and B that I am given in part C, in the pictures there, which is how far does ball C travel horizontally before it hits the ground? That we know. And so we kind of can work backwards in some sense, right? If we know how far it traveled horizontally, and we know how long it's in the air, right? That part hasn't changed. The tabletop is still the same height off the ground. Then we can figure out how fast it must have been traveling. And so that's what we have to do for part C. It's a kinematics thing, right? So we're going to do the same process, right? X final equals X initial plus VI X times T plus 1/2 AT squared. So there's one area that kind of looks weird here, and that's that I've called my distance traveled X, but we're not really just moving in the X direction, right? The 0.15 meters is not either entirely in the horizontal X or the vertical Y direction. And this is mainly just a notation issue. Realistically, and I'm going to rewrite this now for clarity, really what we're writing is the distance we travel, right, doesn't matter the direction. It's still a horizontal distance, regardless of whether it's entirely in the x or y direction or somewhere in between. All that matters is that it is a horizontal distance. So that notation can get a little bit goofy. You might think that you have to take the x component of the 0.15 meters. That won't help, because then you're only going to find the x component of the velocity. We want the whole part, so we have to use the whole distance. So that's one area where you can get tripped up. Again, the acceleration horizontally is 0, so that all goes away. And so 0.15 is 0 plus v initial times, I should get rid of the x there, because we're just saying this is the initial velocity. It's not in the x direction. It's at the 30-degree angle, times 0, that's an ugly 0. All right, that's t. That part hasn't changed. Once again, a pretty easy algebraic equation to solve once you set it up. The setup in this one is, I think, the harder part. And so you rearrange that, and you get 0.31 meters per second. Right, so our speed is 0.31 meters per second. The direction is 30 degrees below the x-axis. We're only asked for the speed, but I just want to make sure it's clear that we're talking about the speed at that angle. And finally now, part D. Calculate the y component of ball A's momentum. Well, first of all, it says momentum in the problem. So we have to either do an impulse calculation, which involves forces, which we don't know anything about, or conservation of momentum. So conservation of momentum is going to be the way we go. But also, if you thought about part C and wanted to use momentum conservation there, and realized you had two unknowns, which is how fast is ball C moving and how fast is ball A moving, well, now you realize you've solved one of those unknowns. You now know how fast ball C is moving. So momentum conservation makes sense to do because you've eliminated one of those unknowns. So the important bit in this problem, before we do momentum conservation, is it says calculate the y component of ball A's momentum. Momentum is conserved independently in the vertical and horizontal directions. And so this means we have to talk about only the y component of velocity, so we only get the y component of momentum. So in our before picture, ball A is moving, but its velocity is entirely in the x direction. So ball A's, and if I start like this, so ball A's initial y momentum is actually 0. Yes, it has momentum. It does not have a y component of momentum there. So 0 for ball A. Ball C is at rest, so that definitely has 0 momentum. So this is a little bit different, right? Even though, yes, ball A is moving, since we're only asked about the y component, it doesn't matter that it's moving in the x direction. So now, after the collision, well, one of these is our unknowns, right? The y component of ball A's momentum. That's, right, I'm just going to leave that. Yes, I could write this as ma times va or something like that, but that's not what we're asked. We're not asked for velocity, we're asked for momentum. So that's our unknown that we're going to solve for, right? That's what we want. And now we need the y component of the momentum of ball C after the collision. So we know the mass of ball C. It's still the same 0.1 kilograms. And now we need the y component of the velocity, right? So if I draw what this looks like for ball C, there's our, let's do it like this. Right, there's our coordinates roughly. There's the velocity that we calculated, right? It's at an angle. And so we only want that piece, right? That's the y component of the velocity. So this is v sine 30 degrees, right? Because that angle right there is the 30 degrees. So when we plug that in to get the y component of the momentum using the y component of the velocity, right? There's the velocity, and then there's the y component. And there's one last thing to do, right? Our y component of the velocity is in the downward direction. It's got to be negative. So, right, we have to add a negative sign in because of the direction. And so now we can solve. And so we properly get that ball A moves upward. We don't know if it's moving left or right, but it's definitely going up in the positive y direction. And we calculate that and plug it in. We get 0.015 kilogram meters per second. Right? So a lot of stuff to kind of pay attention to, especially in parts C and D. They've written the question in a way that can be sort of tricky to figure out the process to follow, but all the steps individually are fairly straightforward.